All right, so here we're going to get a little bit more information about titrations before we do one next class. So this is going to cover pages 10 and 11 in your packet. Don't let that make you too worried. It shouldn't take long. It's some definitions and then some quick calculations. So first, our definitions. What is an acid-base titration? Well, it's just a carefully controlled reaction with a standard solution that we use to determine properties of an unknown. And unknowns and standards are exactly what they sound like. Unknown is a substance we don't know stuff about, so I'm going to try and investigate it and use a titration to learn more about that stuff. Our standard solution is a solution with a known, aka standard, concentration. And then we're also going to use an indicator, and in a pH acid-base titration, we're going to use an indicator that changes color based off of the pH. There's lots of different ones available, but we're going to use one that changes basically at a pH of 7. So this isn't specifically in your notes, but I did want to make sure you knew what equipment we were going to be using in this lab, just so you knew what words and kind of things we're talking about when I tell you to get this materials and start setting it up. So first, most important part of a titration is a burette. This is a very, very carefully calibrated measuring device, which probably looks a whole lot like a graduated cylinder, except it's actually open at both ends. The top is where we're going to be pouring stuff into it, and the bottom has a little valve with a little handle on it that we can use to open and close so that we can pour stuff out into our chemical reaction. And the other thing that is kind of weird compared to a graduated cylinder is that the zero on an burette is at the top, because these are designed to measure how much stuff is poured out in a chemical reaction. So the numbers get bigger as you go down on a burette, so that we don't have to do the subtraction. If I started at 25 and I poured out 3.5 milliliters, then that means I'm at 21.5, and like all of that. We don't have to do as much math because of the way this burette is set up. So we can just read the numbers straight off of the burette, and then whatever calculations we do with those are going to be a little bit simpler. Now, the burette is where our one of our chemicals is going to be. The other chemical is going to be in the flask, specifically an Erlenmeyer flask for our titration. So we put one chemical in one, another chemical in the other, and then they mix as we let stuff out of the burette slowly. Now, the thing holding the burette is a ring stand. It generally has some kind of clampy-do attached to it. And then we, of course, use a funnel to fill up the burette, because it is going to be a very skinny tube and we can't pour into that predictably. So we use a funnel up top and it'll pour things in to that burette. So now let's jump down, back over to that side where we were defining things. When neutralized in a titration, then we say that it's at the equivalence point or the end point. And this is a really important point to find exactly, because that is where the moles of our acid are perfectly canceling and neutralizing our moles of base. So that's when things are truly neutral, and that's going to be important for the calculations we do later. But before we get to that, let's talk about a couple of the different types of titrations we have, because they're going to act a little bit differently. And there's technically lots of different variations of these, even though they all follow the same basic premise we've already set up. So we're actually going to skip down real quick to the question that asks, how does a pH change during a titration? And there's technically two answers to that question, because there's two different ways that we can set up a titration, depending on whether the acid or base is in the flask or in the burette. And before we even talk about those two kind of ways, then it's important to know and keep in mind that we're going to be measuring or observing, graphing the pH change of the flask. We can't measure the actual pH in our burette. It's made for measuring volume, and there's not enough space to measure other things in that same burette. So we're going to be doing all our measurement and observations on the flask. So here in this first situation where I say I'm adding base from the burette to an acid that's in the flask, that means my flask pH is going to be starting off less than 7, because the flask is what has the acid, and that's where I'm measuring my pH. and then I'm going to be adding more and more base, and since the base has a pH greater than 7, that base is going to be canceling out some of my acid and bringing that pH up to be closer to the base level. So in this first situation, my pH would be increasing because I'm adding base to the acid. Now, if I'm adding acid to a base, then that means that my pH in my flask is starting off bigger than 7, like a base, and I'm adding more acid, which has a pH of less than 7. So that'll be canceling out my base, making it go more and more closer to 7, and then once I have more acid in there, it's of course going to dip down lower than 7. So if I'm adding the acid to the base, then the pH will decrease. So there's always technically two different situations that can happen with the exact same acid and base, just based on how you put them into our equipment. So that's going to stay true as we talk about our 3 different general types of our acids and bases in our titrations. Now, this is kind of further investigating that same question. I'm not sure why the strong acid, strong base got above that space. So we'll get to that part in a moment. But as we're talking about these different strengths of our acids and our bases that we're going to be mixing together, what we can kind of envision is like those acids and bases are playing tug of war with the equivalence point, that place where our acids and bases are equal. When you're playing tug of war, whoever is stronger is going to be pulling the rope, or here, the equivalence point, onto their side. So in that first situation where I have a strong acid and a strong base, if both of my acid and base are strong, let's say they're the same strength, then neither of them is winning. Neither of them is going to be pulling the equivalence point onto their side, which means the equivalence point is going to be exactly at pH equals 7. So we're actually going to do 2 quick drawings here, at least for this first one. And both of them is a real quick rough graph here with our pH scale at the left on our y-axis. And we're drawing 2 because we could have one situation like we just talked about where I'm starting with my base in the flask and adding the acid to it, which means that I would be starting with a basic pH, and then as I add acid, it's going to start to decrease until I get to that equivalence point. And then after that, the more acid I add, that kind of flattens out just at whatever pH there is for that acid. Or if I started with the acid in the flask and I was adding the base to it, then that pH would be increasing slowly at first and then really sharply, almost vertically at that equivalence point, and then it would level off again. Technically, this equivalence point should be about halfway through that kind of vertical section of our S-shaped titration curve there. So those are our strong acid, strong base titration curves. Well, what if we had a strong acid with a weak base? If we think of this as tug of war, then our acid is going to win the tug of war because they're strong and the base is weak, which means that our equivalence point is going to get pulled onto the acid side of our pH scale. So here I'm going to do another quick sketch of our pH scale kind of graph here for our titration curve, but my starting point, not my starting point, my equivalence point is going to get pulled farther down towards the acid side of things. And as I draw the rest of the curve, trying to make sure that it's vertical there and that's about halfway through my equivalence point, would look a little like that. So it's a little bit more squished there than the other one was, but it still works. And the important point is that halfway through that vertical section of our S curve is right in the middle at that pH that is less than 7. I technically could have drawn this a little like this as well, but at this point I just need you to draw one or the other, not both of those graphs. So choose one. Now with our weak acid and strong base, base is stronger, it wins the tug of war, it's going to pull the equivalence point onto that base side of things, which means that our pH at our equivalence point is going to be bigger than 7. And if I drew that on my titration curve, then I'd be adding an acid to my base and bringing this over and down that looks a little bit more accurate. I'm not going to be asking you to draw these out. Mostly recognize where the equivalence point would be with different combinations of our strong and weak acids and bases. So that finishes out our page 10, and if we can jump over to page 11 real quick, we're going to come back to this idea that at the equivalence point, our moles of acid are equal to our moles of base, and we're going to get an equation to write out to use to help solve those three problems, because they are pretty quick, simple problems. And don't worry, just because we are going to be finding moles, we're not actually doing any dimensional analysis or stoichiometry here. All we're doing here is kind of using that molarity formula or equation, solving it for moles. That means molarity times volume. And if we plug that in for our moles of acid and base, then I have my MAVA, molarity and volume of my acid, set equal to MBVB. This is the equation that I need you to write at the top of the page there. This is the equation we're going to use to solve all of our titration problems. And it probably looks pretty familiar because our dilution equation was M1V1 equals M2V2. So it's the exact same idea with this equation. It's just with an acid and a base instead of with one solution turning into a second one. And still, as always, we can solve for any of our unknowns by taking the opposite side of the equation and dividing it by any of the unknowns' neighbors. So, to put this into practice in that first example here, it says that we have a 15.5 milliliter sample of 0.215 molar potassium hydroxide solution. And since potassium hydroxide is a base, then that first volume and molarity is the VB and MB. And that's how much is required to titrate 31.2 milliliters of our hydrobromic acid. So that is our volume of our acid. And it wants us to calculate the molarity of our acid. It's the one that was missing, MA. So I can rearrange and solve for MA. The opposite side of MA's equation is MBVB, and then divide by MA's neighbor, which is VA. And since I had just found all those numbers, we just need to multiply and divide, get our answer. Here all of my numbers were 3 sig figs, so I just want to round this to 3 sig figs, and my 8 will round the 6 up to a 7, and 0.107 molarity is our answer. And the next question is honestly very similar. Different words, different numbers, but here we're also being given the volume of an acid that is neutralized by a specific volume and molarity of this base. Trying to find the molarity of our acid again, plug in our numbers in, and when we get this answer, even though it's different, we are going to be rounding this to 3 sig figs. All of my numbers here had 3 significant figures, so I just want to keep these first 3, and just like the last one, the 8 is going to round our 6 up to a 7, so our final answer is 0.0257 molar. This last example is a little different. It is asking us to find volume of this base solution here. So I have the molarity of my base that is required to neutralize this volume of this molarity of my acid. And so even though I am solving for my volume of my base, which is like the opposite thing of what I was solving for before, I'm still multiplying together. So the numbers that go together, dividing by that third number that I've got, putting those all together gets me my raw answer. Looking at all the numbers that I was given, I had 2 sig figs, 4 sig figs, and 3 sig figs. So this time when they don't match, we keep the least number of sig figs that we were given and putting together. So 2 sig figs in our answer means our answer is just 45 milliliters. So hopefully not too bad. Hopefully kind of familiar to the calculations we'd done before. We just need to be able to apply them to acids and bases.